Okay, we're now ready to prove the big theorem connecting kernels and images of linear maps, and it's called the rank nullity theorem. Before we do so, we've got a couple of things that we need to prove. So first of all, a proposition which says that a linear map from V to W is injective if and only if its kernel just contains the zero vector. So first of all, let's suppose that T is injective and prove that its kernel must be just the zero vector. So we've already proved the following fact about all linear maps. They send the zero vector in their domain to the zero vector in the codomain. So if T is injective, the only thing that it can send to the zero vector in W is the zero vector in V. But that says exactly that the kernel is just the zero vector in V. So that gives one direction. For the converse, let's suppose that the kernel of T is just the zero vector, and we're going to prove that T is injective. So we'll suppose that T of x and T of y are equal for some vectors x and y in V, and for injectivity we've got to prove that actually x must be equal to y. But the thing is, we can use linearity to do that. If you've got T of x is equal to T of y, then you can subtract from both sides to get T of x minus T of y is equal to 0. And you can think of that as T of x plus minus 1 times T of y is equal to 0, or equivalently, T of x plus T of minus y is equal to 0. Of course, I mean the zero vector in W every time. But then by linearity of T, what you've got there is T of x minus T of y. So that takes us to this step here. T of x minus T of y is the zero vector in W. That says that x minus y is in the kernel of T, but the kernel is, by assumption, just the zero vector. So x minus y equals the zero vector. In other words, x minus y is equal, x is equal to y. So that gives us injectivity, so we've now done both directions of this proposition. Okay, now we really are ready to do the rank nullity theorem. So here's the definitions. The rank of a linear map is the dimension of its image, and the nullity of a linear map is equal to the dimension of its kernel. Let's recall some examples of kernels and images we did in the last video. So example 1, if we take A to be the matrix 0, 1, 0, 0, and TA to be the linear map r squared to r squared, which is left multiplication by A, then we saw what the kernel and image were. In fact, they were both the same. The kernel of TA and the image of TA were just the set of all vectors like this. And that, of course, is a one-dimensional vector space. The reason that it's one-dimensional is that it's spanned by the vector 1, 0. Every element of the kernel or the image is a multiple of 1, 0. So that single vector forms a spanning set, and certainly a single non-zero vector on its own is linearly independent, so it's a basis for the kernel and the image. So we've got the dimension of the kernel and the dimension of the image are both equal to 1. The rank and the nullity of TA is equal to 1, and if we notice that the rank of TA plus the rank plus the nullity of TA is equal to 2, which is the dimension of the domain r squared of TA. Let's look again at another example we've seen recently, which was the differentiation map. So D was the map from R less than or equal to n of x to R less than or equal to n of x, given by D of a polynomial f is the derivative df by dx then we saw that the kernel of D was the space of all constant polynomials. So the kernel was a vector space of dimension 1 because it was spanned by the constant polynomial 1. So the nullity of this particular linear map D is equal to 1. We also worked out the image of D. The image was equal to the set of all polynomials of degree at most n minus 1 in X. So this thing has got dimension n because there is a basis 1x, x squared, up to x to the n minus 1. So n things. And that means the rank of D is n. And again, in this case, if you add the rank of D, which is n, to the nullity of D, which is 1, then you get the dimension of the domain of D, n plus 1. We're going to see that the rank nullity theorem guarantees that always happens. But before we prove rank nullity, okay, one more partial result, which is just a note about linear maps. So the definition of a linear map from a vector space V to a vector space W was that it was a function t satisfying t of x plus y is t of x plus t of y, and t of ax is a times t of x for any elements x, y in the domain V and any scalar a. But you can use these parts of the definition multiple times. So if you have a linear combination like this one, you can use the linearity definition a lot of times to get that if t is a linear map, then t of this linear combination is a1 times t of x1 plus a2 times t of x2, and so on up to an times t of xn. And that works whenever you've got scalars a1 up to an, and whenever you've got elements x1 up to xn in the domain V of t. So we could write this in sigma notation. In sigma notation it says t of the sum of ai xi is equal to the sum over I of ai times t of xi. We'll use this without comment from now on. So we're ready now to state the rank nullity theorem. It says that if you have a linear map T from a vector space V to a vector space W, then the dimension of the image, which of course is the rank of T, plus the dimension of the kernel, which of course is the nullity of T, is equal to the dimension of the domain of T. Let's think about the proof. It's actually quite easy for us to do this because of all our work that we've done on extending things to bases. So you'll remember the extension to a basis result, which says that if you have any linearly independent set, linearly independent sequence inside a finite dimensional vector space, then you can always extend it to a basis of that vector space. So here we're assuming that V and W are finite dimensional. So let's write this in. V and W here should be finite dimensional vector spaces, FDVS. Okay, so here's how the proof goes. We take a basis for the kernel of T, and we'll call that K1 up to Kn. That is a linearly independent sequence inside V, so we can extend it to a basis of V. So we'll do that and introduce notation for the extra vectors we have to add in to make up a basis of V. We'll call those V1 up to Vm. It's then enough to prove that T of V1 up to T of Vm is a basis for the image of T. Because if we proved that, then we'd know that the dimension of the image was m, because T of V1 up to T of m is m things forming a basis. The dimension of the kernel, we'd know that was n, because that was the notation we used for the size of the kernel of T, the size of a basis of the kernel of T. And we'd know that the dimension of V was n plus m, because here we took n linearly independent vectors which were a basis for the kernel and extended them to a basis of V, and we used m as the size, the number of vectors we had to add to those n vectors which were a basis of the kernel to get a basis of V. So this will be n plus m. So if we were able to prove this result, then the dimensions on would be correct for the statement of the rank nullity theorem to be true. So that's all we have to do. We have to verify that T of V1 up to T of Vm in this notation is a basis for the image of T. So we have to prove that that sequence of vectors is a spanning set for the image of T and is a linearly independent sequence. I said spanning set, I should have said spanning sequence. Okay, so let's prove that T of V1 up to T of Vm is a spanning sequence for the image of T. So we'll take any vector in the image of T, so T of some element of the domain of T, and we have to prove that that is equal to a linear combination of T of V1 up to T of Vm. But what we know is that the vectors k1 up to kn and v1 up to vm are a basis of V. So we can write the V here as a linear combination of the k's and the v's. So we'll do that. V can be written as a linear combination of the k's and the v's, where the scalars involved in that linear combination, we'll call those a's and b's. And now we can use our linearity. So linearity of T tells me that T of V is T of this linear combination, and we can move the T through the sums. So we get the sum of AI times T of Ki plus the sum of Bi times T of Vi. That's coming from the comment I made on the last slide. But of course, the k's are kernel vectors. T of Ki is always 0. So that first sum is just the 0 vector lots of times, so we can ignore it. And what we get is just the sum of Bi times T of Vi. And of course that, by definition, is an element of the span of the T of Vi's. We've proved that an arbitrary element of the image of T is a linear combination of T of V1 up to T of Vm. And that shows that T of V1 up to T of Vm is a spanning sequence for the image of T. The thing that we have left to do is linear independence of T of V1 up to T of Vm. So let's suppose that we have a linear combination of the T of Vi's equal to the 0 vector in W, and then we have to prove that actually all those coefficients, A1 up to Am, must be equal to 0. Again, we're going to use linearity. This linear combination, sum I of AI T of Vi, is equal to T of the sum of the AI Vi's. That's just an application of the extra comment about linearity we made on the last slide. And that's telling you that the sum of the AI Vi's is an element of the kernel of T, like it says here. If it's in the kernel of T, well, we have a basis for the kernel of T, which is k1 up to kn. So every element of the kernel can be written as a linear combination of the k's. So when we do that, we can write the sum of AI Vi as a linear combination of the k's, let's say the sum of the Bi ki's. But now if you rearrange that, you've got a linear dependence on the vectors V1 up to Vm and K1 up to Kn. But those things are supposed to be a basis of V. In particular, they are supposed to be linearly independent, and that means all of the A's and the B's must be 0. In particular, all of the A's must be 0. And that means we've shown that the T of Vi's are linearly independent. We started off with a linear combination, sum over I of AI T of Vi being the 0 vector, and we proved that actually all the A's must be 0, so that's linear independence of T of V1 up to T of Vm. We're done. That's the rank nullity theorem.